All right, welcome to compounds and their bonds. So this is a pretty long PowerPoint. Imagine it's going to be probably 7, 8, maybe even more segments. Again, I'll try to keep it down to 15 to 20 minutes and we'll break it up where we can. In this section, what we're going to be looking at is the octet rule and ions. So up until now, all of our protons and electrons have been equal. Now we're going to start to mix it up a little bit. Our electron is going to change the electron count. Protons, remember, will have to remain a constant. We'll look at ionic compounds, and then where it gets time consuming is going to be the naming and writing ionic formulas. We'll look at some polyatomic ions, covalent compounds, and then we'll switch gears to electronegativity and bond polarity, shapes, and polarity of molecules. Those last two sections are going to switch up a little bit depending on whether or not you're in Chem 110 or Chem 100. So basic Chem, we won't be worrying about shapes or polarity of molecules. We'll only be looking at electronegativities and bond polarities. For Chem 110, General Chem, you will be doing pretty much all of that and then trying to discover whether or not a molecule is polar based upon the electronegativity and the shape. All right, so either way though, we're going to start by how we keep track of our electrons. So up to now we've been doing electron configurations, we've looked at electron arrangements, both of which give us great detail to where the electrons are, but it's a little bit cumbersome and there's a lot more information there than what we actually need. So as it turns out, what we care about are only the electrons that are responsible for chemical properties, which are the ones in the outer energy level. So we don't worry about all of the electrons, just the ones in the outer electron levels. So if we're looking at electron configurations and we've got 1s2, 2s2, 2p6, 3s2, 3p4, we don't care about energy level 1 or 2. We only care about energy level 3 because that's the outermost energy level. The electrons in that outermost energy level are referred to as the valence electrons. Now we're only going to be looking at this for our main group elements, so we're going to be looking at our 1A through 8A only. Okay, that's going to make up our octet rule. Now valence electrons are the ones in the outermost energy level. Everything underneath of that outer energy level is called a core electron. Well, if we know that we might have 50 some electrons, but only the last 8 are the ones that matter, then I don't really want to keep track of all of them. I just want to keep track of those last ones. So what we're going to do then is look at what's called an electron dot arrangement. Here, we're going to worry about the atoms in the same column, that last column, that outermost column. Those are the ones that we're going to worry about because that's going to give us the same electron configuration, which means we have the same number of valence electrons. So when we're looking at reactivity, the reason why all of the group 1A will react the same way is because they all have one valence electron. And again, knowing that it's one valence electron is going to be easy by looking at just the groups on the periodic table. So 1A would be one valence electron, 2A will be two valence electrons, 3A, three valence electrons. You get it, right? 5A would be 5 valence electrons. So group 2A, beryllium, magnesium, calcium, doesn't matter which one it is, all of them, because they're in 2A, will be 2 valence electrons. That means that I'm looking at diagrams with no more than 8 electrons in them. So I don't care about the 1s2, 2s2, 2p6, 3s2, 3p6. All I care about are those last energy levels. What's in the third energy level? Well, turns out that the group number tells me how many electrons are in that last level. Now remember, this is only for the A elements, so 1A through 8A. This does not work for transition metals or intertransition metals. Okay, now how do I draw then these electron dot diagrams? Well, again, it's an easy way of keeping track of just the valence electrons. So the first thing we're going to want to do is write the symbol. Then we're going to put one dot in for each of our valence electrons. Now, we won't pair the electrons up until we have to. So the way we do this is we think about an element X, and what we're going to do is put in an imaginary box. So we're going to put our element symbol in an imaginary box, and then we're going to put electrons on the sides. So this would be 1, then we'll do 2, then we'll do 3, then we'll do 4, 5, 6, 7, and 8. Now, that's what this last bullet's telling us. We don't pair them up until we have to. So you notice I started here and I just went clockwise. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's all we're going to do. Let's try one. We're going to do nitrogen. Oh, let me turn the pen off. There we go. Let's try this again. So we'll do nitrogen. Okay, so we're going to have 5 valence electrons because nitrogen's in 5a. And the first thing we want to do is just write the symbol. So the first symbol for nitrogen would be a single letter. It's a capital N. Now, all we're going to do is add 1 electron to each side one at a time because we cannot pair them up until we have to. So I'm going to put in the first one up top. Then I'm just going to go clockwise, but you don't have to go clockwise. They can go anywhere you want as long as you don't pair them up. So 2, I'm going to go there. 3, back down to the bottom. 4 to the left. And that takes care of 4 out of 5. Now the 5th one, I don't have a choice. I have to pair it up. Now I just like to keep the format going, so I'm going clockwise. I'm starting at the top. So I'm going to put my 5th one up here at the top like that, but you could actually put your 5th one anywhere you wanted. Now, we've made a pair up here. This pair is referred to as a lone pair. Oh, not sure what the heck I just did there. Let's try turning the drilling off and see if that fixes it. It does. Not sure what I did, but this was supposed to be lone pair. Now, lone pairs are also referred to as non-bonding pairs. So guess what they're not going to do? Correct. They're not going to bond. Okay, so single electrons will perform bonds. We'll see that by the end of the chapter, but pairs will not. So we call that a non-bonding pair or a lone pair. All right, so that's electron dots in a nutshell here. So let's just try a few and see how we do. So write the electron dot pair for sodium, magnesium, carbon, oxygen, fluorine, and neon. So you might want to pause here, give yourself some time. I'm going to go right into it. So we have sodium, and then of course it's in group 1A, so it gets 1 dot. So I'm just going to put a single electron right at the top. For number 2, we have magnesium. Magnesium's in group 2A, so I'm going to have 1, 2 dots. Now again, you can have your 2 dots anywhere you want it around the magnesium as long as they're not together. Carbon is in 4A, and your carbon has to look very much like my carbon. So we have 1, 2, 3, 4. Then for oxygen, we're going to have group 6A, and so this is going to be 1, 2, 3, 4, 5, 6. For fluorine, we're going to have 7A, so we have 1, 2, 3, 4, 5, 6, and 7. So I have 3 pairs and 1 single electron. For the oxygen, we had 2 pairs and 2 single electrons. So remember, we were making lone pairs here. These are going to be our non-bonding pairs. And so what we're going to find out is fluorine can only make 1 bond. Last but not least, we have neon. Neon is in group 6A, or excuse me, 8A, has 8 valence electrons. So I have 1, 2, 3, 4, 5, 6, 7, 8. And that's a noble gas. And of course we have 4 pair, so it's not going to make any bonds. All right, you can kind of see in the view here, I have helium is going to be our next one. So I'm going to go ahead and write that out, helium. And I'm going to give you a moment here, maybe pause, because helium is going to do something special. Now we said you can't pair them up until you have to, but helium is going to be our exception. We're going to pair them up just like that. And again, that's because it's an 8A. Remember, hydrogen and helium can only hold 2 electrons. So I actually cannot hold 8. I can only hold 2, and so we have to pair them up right away there. All right, so those are electron dot structures. I hope you did well with those. Pretty straightforward, I hope. All right. So the next thing I want to get into is atoms and ions, which is going to walk us right into bonding and looking at naming. And so we're probably going to go another 5-10 minutes and we'll have to pause again, and then we'll get into some naming probably. So atoms, again, are going to be electrically neutral. So we have the same number of protons and the same number of electrons. Now ions, which is what our new focus is going to be, are going to be atoms or potentially even groups of atoms that have a charge. That means we have a different number of protons and electrons. Now remember, back to the last segments, protons can never change. Neutrons, when they change, they make isotopes. Now we're going to be looking at making ions, which means only the electrons can move. Okay, protons cannot move. Only electrons can move. So we're either going to gain or we're going to lose electrons. Now, depending on which one we do, we're going to get a specific name. So the first name we're going to get is going to be an anion, a negative ion. So it's right there in the name. A negative anion, a negative ion. To make a negative ion, I'm going to either have to gain or lose electrons. Now remember, the protons are going to stay the same. So if I want to make a negative ion, I have to gain electrons. This typically messes with us because when we think of positive and negative, we think of emotions. I'm positive, yay, I'm a happy person, or I'm negative, oh, that was bad news. But when we get something, when we gain something, we tend to think that's positive, right? Because it makes me feel good. Oh, I got a Christmas present, yay, lucky me. Well, here, that's not how it works. Chemistry does not work that way at all. What we're looking at is we have a negative ion, and we gain that negative ion. That means we're going to become a negative charge, right? So here we have the gaining of electrons is going to give us a negative ion, an anion. Now, only our nonmetals can gain electrons. So metals always need to be positive. They can never be negative. Now, remember, when we were writing our symbols a bunch of segments ago, where do we write that symbol? So if I know I have an element, it has an atomic mass, it has an atomic number. Those are both on the left, up and bottom. What about the charge? Well, the charge goes on the top right. So it's going to be a superscript on the right side. So for instance, if I'm looking at fluorine, and fluorine's a -1, notice the -1 charge is in the superscript on the right side. Okay. Now, what does that superscript tell me? Well, it's a -1. That means I've actually gained 1 electron. Oxygen raised to the -2 means it's done what? Well, it's gained 2 electrons. Hopefully that makes sense, right? So we've gained 2 electrons as oxygen, so we get a -2 for a charge. We write that as a superscript on the right. Now, what happens if we don't gain electrons, but we lose them? Well, if we lose them, that means we formed a cation, right? So a cation is a positive ion. It's the cathode, it's positive, that's where the cat's coming from. So it's not the animal, it's not a cat, it's not a feline, it's a cation. Now, positive ions, these are going to be formed by losing electrons, which means you have more protons than electrons. And again, that's going to be the metals. So remember when I said you want to know that stair-step line on your periodic table? This is one of the reasons why. Anything to the left of that stair-step is going to be a positive ion. Anything to the right of the stair-step is going to be a negative ion. So it's telling you already the difference between your metals and your nonmetals, and now the differences in your charges, positive or negative. The symbol is the same way. So here we have potassium with a +1. That's telling us that the potassium has lost 1 electron. Calcium with a +2 means calcium has lost 2 electrons. So far, so good, I hope. Now, one of the questions students typically have at this point is, well, how did I know potassium was going to be +1, or calcium was going to be +2, or fluorine was a -1, or for that matter, what's the charge of aluminum? How am I going to know what the charge of aluminum is? It's not on any of these lists, Mr. Caro. You didn't help me out with that. Well, charges on ions, for the most part, group A elements, it's very correlated with the periodic table. By looking at the periodic table, you're going to know the charge, and I'm going to give you a diagram in the next slide for that. Elements in the same group, again, will have similar properties. We saw this. They have the same number of valence electrons, which means they're also going to have the same charge. Okay, so how does that work out? Well, here's your periodic table. Group 1A, we see we have a +1 charge, all of them. Group 2A, you have a +2 charge for all of them. Now remember, this is only going to work for our main group elements, so we're skipping all of the transition metals. We're not worried about any of those. Notice I even left the inner transition metals off of this particular table. Group 3A, boron is left blank, but the rest of them are +3, so that aluminum would be a +3. Boron, we're not going to worry about boron. You can actually take an entire semester course learning about boron by itself. All right, so if you're a chemistry major, as I was, I took a course on boron my senior year as a chemistry major. Okay, and the whole course was nothing but boron. We obviously don't have time to get into all of that stuff here, so we just omit it. We don't worry about it. For group 4A, remember that stair-step line cuts kind of right in the middle of it, and that means 4A kind of does funny things, and we're going to leave 4A out of it. We're not even going to worry about 4A right now. I'll show you some ways to know the charges when you need to know the charges as we talk about naming. But as a rule of thumb, it could be +4 or -4. It's really going to depend on what's going on. For group 5A, we're back to a -3 until we get to that stair-step line. Okay, so here we have nitrogen, phosphorus, and I believe that's arsenic. Arsenic, I left that one black because it can be +5 or -3. Remember, it's on the stair step, so it's a metalloid. For us, when we see it, it'll be a -3. I try to avoid it on assessments. That way you're stuck with just nitrogen or phosphorus, and you know it has to be a -3. For 6A, we have -2, again, until we get to that stair step line. Then we start to do funny things in beryllium. And then finally, once we get to 7A, it's back to normal. Everything in 7A is a -1. All right, so now how do I write electron dots for anions? Well, very similar to writing electron dots in general, except now, right, if I'm looking at phosphorus, phosphorus has 5 dots. I go back to my periodic table, phosphorus was here, it's going to make a -3 ion. So what's that tell me? Well, that tells me it's going to gain 3 electrons, right? So there's 1, there's 2, and there's 3. We're going to fill that in. It's going to form an 8 electron surface here. So our outer energy level will have all 8 electrons. And the way we'll denote that is by writing phosphorus with a -3 charge. We're also going to change the name, and we'll see what we're going to do that in the next segment. Now, what about cations? Well, metals typically have fewer electrons, which means you don't have all of your electrons there. So let's take a look at calcium. Calcium has calcium is a group 2A, so it has 2 valence electrons, 1, 2. If we flip back to that periodic table, oops, a little too far there. I'll get it sooner or later. There we go. So calcium is in group 2A, and we know group 2A is going to make a +2 charge. So skip back forward here. Since we know calcium is going to form a +2 charge, then what that's telling us is that we need to lose those 2 electrons. And so there they go. Once we lose them, it's going to look like calcium has no valence electrons, but that's not true, right? What's really happening? Well, if I lose those 2 electrons and I form a +2 ion, what's actually underneath of that is still a full energy level. And that's the goal here. So what the elements are trying to do is form stable electron configurations, which means they basically want to have the noble configuration, the electron configuration of a noble gas. Now remember, noble gases are in group 8A, which means we're looking at 2s and 6p electrons, right? And this maybe should be superscript. I don't mean to confuse anybody here. We need 2 electrons that are in the s and 6 electrons that are in the p. These are not meant to be coefficients. So I'm not saying that we have to have electrons in the 2nd energy level of S and the 6th energy level of P. That would make no sense. What I mean is we need 2 of these and 6 of those on any energy level, because that will give us 8 valence electrons. Now once we have 8 valence electrons, we are following what we call the octet rule. And so therefore our electron configuration will look very much like a noble gas, where we have 8 outside electrons. All right, so hopefully that's making sense so far. We're going to build from here to start talking about different types of compounds. So the first type is molecular compounds, but we're going to get to that a little later. We're not going to worry about that. We're going to start with the second type, which are going to be our ionic compounds. And so we'll start there. Since we're talking about charges, I want to get into looking at ions and how the ions will form compounds. And so that'll be in our second segment. All right, stay tuned.